Cliff Kancler, who retired as a senior consulting engineer. He's a Lockheed fellow and very distinguished 40-year career here, and he'll tell you a few of the good things about the company.
So this is just like working at Lockheed, because it was always the data processing guys that got squeezed at the end of all the presentations. And all the time was gone. This is a picture of the plant. I have wanted to show you this because I arrived a couple of years later, and there's the plant, and the parking lot is full, and we're surrounded by tomato fields. And now you got Ariba and Yahoo and Juniper there, so we were like the anchor, the store anchor in a mall or something like that. Everything flocked around us. Move on. So I want to give you the perspective of a young engineer graduating in 1965. I've got a degree from Rensselaer. I just spent 4 years going uphill in the snow to my classes for 4 years, and it was pretty cold. And upon graduation, I wanted to get a job that didn't get me killed. That is actually a graduation card that one of my friends gave me is, here's where your career is going, son, if we don't do something. So Sunnyvale sounded pretty good, but just in case I wanted to have a fallback, we always needed a fallback, and so Boeing out in Seattle was my fallback. And they were offering $145 a week. I suspect some people make that hourly these days. But at the time, that sounded like a lot of money. I did not know how I was going to spend that much money. Anyway, I finally got the job at Lockheed. Next chart. And since they were hiring 19 new people a day, I figured I really had to screw up not to get hired. So I got in, and it wasn't like squeaking in either. There were actually billboards on the Bayshore Highway advertising this, 19 new people a day. They had a thing set up on Matilda where they were just processing people. So I got here, I got my job. Next week I went out and bought a bright new red GTO. I got an apartment on Easy Street. My father loved that, Easy Street. The guys in the apartment next to me had a tiki bar set up in their apartment, and they had a Cadillac hearse. And I'd be getting up in the morning, and I got my suit and tie on, going to work, and they were loading up their Cadillac hearse with surfboards heading out to Santa Cruz. So that was the whole California experience right there. I thought, wow, I've arrived. But then I got to work. There was never a day where I didn't want to go to work, but next slide. But these guys were scary smart. The technology wasn't all that sophisticated, but the way that they used the technology on Polaris and Poseidon was just so clever. You know, you just had to admire the people who you're working for. Dave Montag hired me into the FBM program. It was like the luckiest day of my life. Now, I got to be a computer guy, and I figured, well, gee whiz, why did that come about? Turned out all my bosses were analog guys, and I'd had a course in Fortran, and I took some logic design course, and here I was, the young guy, so they figured, hey, it's got to be the computer guy. We don't know anything about it. So I was happy to go with that point of view. On Polaris, I wanted to mention they just had transistors for logic, and as Dave mentioned, it was implicit guidance. It was this very clever use of, anybody ever heard of a digital differential analyzer? A couple of people, I guess. I think they actually use some of this thinking in graphics these days, but back then it was just an integrator, and you fed the overflow to other integrators so you could solve differential equations. So it was extremely clever. It was quite efficient, given that they were implementing it with transistors. And then Poseidon, as Dave also mentioned, they went to explicit guidance where you calculated a velocity vector to hit the target. And now you really needed an actual computer, one that could run a program and solve equations and things like that. And MIT Instrumentation Labs later became Charles Draper Labs. had been doing all of the Apollo work. So they had their own clever side of things. Their read-only memory was wires woven through transformer cores. They used a core memory to get to the moon, but for our environments, we needed a different kind of technology, plated wire. I brought both of these books here. You can kind of peruse them if you wish. I was thinking about passing them around, but way too many people to do that. People made do with what they had available, and they did very well with it. Again, as Dave was saying, we had this bus that we flew around the sky, and people figured out that there was this chain of resolvers in the guidance gimbal assembly that if you just ran an 800 hertz signal through it, you could get from inertial coordinates out to missile coordinates, which is where we needed to be to do flight controls. And then there was another vector that ran at 90 degrees, or another waveform that ran at 90 degrees to that. So we demodulated these P and F vectors, and we had all the stuff we needed to fly our bus around the sky. Okay, my turn came in 1972. I did become the computer guy. We had won a trade-off within our department as to whether we were going to implement the flight controls in digital or analog. And digital won pretty much on all counts, but mostly the flexibility. And I guess I just want to point out, because this is a very complicated chart, you dive into it, but you don't really need to. The entire instruction set is right here in this big block of stuff. That was it. That was all you had to know in order to program the computer. I broke out a part of it. The little bit of cleverness here is multi-use of an instruction that I'd mentioned. Here's one instruction that does three things. It's like a over the square root of b, and if you square the denominator, you get a divide, and if you divide a thing by the square root of itself, you get a square root, and so on. So the architecture we put together was extremely efficient. This should blow your mind. We had exactly 5,000 bytes of read-only memory to do all the functions that I've listed out there. All the thrust vector commands, we mixed different kinds of data to get the accurate gyro data. We had digital bending mode filters. We're pulse width modulating valves to fly around the sky. It was very cool. Next chart. You can hear me rustling the papers, right? So because that's the cue. So state-of-the-art design-wise in 1972 was a very sharp pencil on vellum. I got to tell you that stuff holds up well because I still have the vellum. Still looks good. That green thing up there was something I found in a cabinet back when I was looking for a way to draw things. And if you look at it closely, you'll find it's a mill standard template. And it's got tetrodes and pentodes. And oh, by the way, it does have transistors on it too. So that was my design guide there. Cool stuff that the department picked up later was an HP 35. And you had to check it out from the department administrator. Remember that? You were yeah, because they were very expensive. They cost a couple $100.
$385. Did you know that Steve Wozniak worked on that?
I did not know that.
Yes.
I did not know that at all. One of my instructors at Santa Clara, I think, also worked on it, but he wouldn't talk about it at the time when I was there. There was no design library. The design library was a TI yellow book, 5474 MSI stuff. I'm sure a lot of people are very familiar with that book, and you just looked at it and, you know, here's the pinout, put a symbol down and pin it out. If you wanted to simulate it, well, you thought very hard about what was supposed to go on. That was simulation. We did not have design simulators. So that's the tools of the trade. This is 1972. In 1975, we had a package. We flipped the chart. Yeah, we had a package, a substantial thing. I don't know, weighed 30 or 40 pounds or something like that. These were heat-sunk boards. They were very sturdy. And there was a lot of analog stuff on here as well as all the digital stuff. I got to design the digital stuff, but there was a whole department that put together the analog. component. So there's power supplies on there and valve drivers and things like that. I want to point out that that TI stuff, we had to have hardened versions of it. So we went to, I think it was Raytheon, they checked me on that, and we went to Raytheon and we had 10 chips that we had to get hardened versions of so we could put them on the boards. So all that had to happen in this time period. We had to take that stuff from TI, give it to another supplier, get it hardened, get the chips tested back and onto boards. And then once it was on the boards, we only had read-only memory. So we had to be something like a year before the flight and deadly accurate in order to not hold up the flight. Nobody wanted to do that. So these were very compressed schedules, but I gotta say it was a lot of fun, busy all the time. And let's see, from 1972 to January of 1977 we flew the first Trident, and it was a total success, according to the Navy. I still have the newspaper, got it there on the bench. And something like 8,000 people were employed at Lockheed just for this program at the time. Really good program to work on. And it went on, we had 40-some successes in a row on Trident 1, and there were hundreds, I believe, on Trident 2. So these were very reliable missiles. Fun stuff, did have some fun stuff. It was all fun to me. But engineers are like that, right? No floating point. So I had to put pencil to paper and go through all the equations and make sure there was never an overflow, no matter what possible combination of numbers there could be, and that we didn't lose significance. So it was an arduous process because we're just moving bits around in 16-bit registers rather than, the guys today, IEEE 754 floating point, cool. Not us. And I pointed out to my boss that we really weren't exercising the numbers in the computer to the extent that they should be because we only had this one program. I said, I got this great idea for a program, flipping to the next chart briefly. Over at Stanford, they had this thing called Space War. And I went over to, I don't know where it was, I think it was in the Union or something like that. It had been running for years. And I looked at it and I said, I can do that. There's a couple ships flying around, they had thrusters, you had attitude control, you could shoot torpedoes at the other guy. And you went around a central sun, so you had gravity working for you. You could do hyperbole and things like that. You could go off the screen and sneak up on the other guy. Brought it back to my boss and said, this'll do it. This'll work all the numbers in the computer. We're really gonna work the arithmetic unit. And it was a big hit. We had these family days where we brought the kids into school, into the lab, and there was a line out the door. And I was not the guy, unlike somebody in this room, I was not the guy that knew that there was a lot of money to be made there. I looked at it and said, well, that was a lot of fun, but I got a pretty good job. So it came and it went. And at the time, there was nothing. There was, Intel had a 4004 processor, and there was Palm. It says up there, Palm. That was it. So the Space War thing was wow. Eventually, my boss had to confiscate the paper tapes that we used to load the program because the engineers, when nobody was around, would be playing Space War. A couple people in the room were partners to me on the last couple of programs I worked on. This was one that Dave wanted to see done. It was computer avionics that would be flexible across a whole lot of programs. So we got to put this in underwater missiles. We got to fly the last flight to the moon, Lunar Prospector, on a Lockheed launch vehicle. And I believe there are still some of these packages floating around in interplanetary space today because the Palo Alto labs used them in a Star Tracker. So, space of 30 to 40 years. Probably the last thing we did was 2002, we built this 1,000-element image processor. Every element was more powerful than our little 16-bit processor that flew Trident. In 2012, here's an Arduino processor. It sells for $10, and it's probably 100 times more capable than that package there. And on the last note, this technology is wonderful because my daughter got me here on her little iPod, punching in things on ways to say, turn here, turn there, and we got here on time. So thank you very much.